Okay, so just a couple things. I did post solutions yesterday to the practice exam I wrote. So if you were looking for those, they're on Canvas. Are there any questions at all for those of you that have a midterm today that you would like me to cover? Or I could say more generally, any specific topics or types of what you'd like to see before we start talking about double integrals. The floor is yours. How many of you have a midterm today? Couple of you. Okay, so less than half of people who are here. Welcome, Jennifer. All right. So if you change your mind, I'm certainly happy to go back and address things, but we will move on talking about some double integrals. Also, I have office hours after this class from 1 to 4. I know your exam's at 3, so if you want to come over to CADS and get some help preparing. I mean, I imagine most of you are probably already prepared for your exam that's in a couple hours, but if you have any last minute questions, I'll be over there. So let's go ahead and talk about where's my double integrals. Yeah. Which part of me is kind of wonders why they include this material in this class. Like it just feels kind of like we talk about it for a second and then goodbye. And then we don't do it again. Like we don't really use it for anything, I think, later on in the course. Like it's not helping us build something up. It's probably just something they decided you're supposed to learn in calculus at some point, and this is where they stuck it. So we'll talk about it for a moment, and then we'll be done with it. Today is, sorry, this is Co-17C. Today is April 25th. Not too hot, not too cold. So, pens. All right. Sorry, I'm having some pen issues here. Here's what we're going to do first. So, we're going to start by finding the area in quadrant 1 between the curves f of x equal to 4x and g of x equal to x cubed. And we're first just going to start off by doing it kind of what you would think of as the normal way, using a single integral. So first, using a single integral. So let's draw the region. We know what the cubic function looks like. It looks vaguely like this. And f of x equal to 4x looks something like this. So I'm trying to find this area here between the curves, right? Because I'm in quadrant 1. So my lower function is g of x equal to x cubed. My upper function is f of x equal to 4x. And this point of intersection here, let's see if x is 2, both functions equal 8. You could also find that by setting them equal to each other and solving, but I already knew what it was. So one way we could write this would be the area between the two curves is equal to the integral from as far left as x equals, oh, sorry, I should say one more thing here. I'm thinking about using vertical cross sections for the way I'm about to do it. So I know it's been a minute since we've done integrals, but the idea here is that we're adding up all these areas of rectangles. The area of that rectangle is the height, which is 4x minus x cubed, times the width, which is dx. So we're integrating 4x minus x cubed, the height, times the width. And then when we integrate, we are adding up all those areas to get the total area. We're going as far left as 0, as far right as 2. We could also do it using horizontal cross sections if we wanted to, where we do things in terms of y. We could say, okay, we're going to go from as low as y equals 0 to as high as y equals 8. And then the area of my rectangle is the length, which is the right function minus the left function. The right function, instead of writing y equal to x cubed, we're going to write x equal to the cube root of y. Instead of writing y equal to 4x, which I know you can't really see there, we're going to write x equal to y divided by 4. So then the length of the strip is the right function minus the left function, which is the cube root of y minus 1/4 y, or y over 4, times the width, or I guess technically the height, which is dy. So those are two ways we could write this integral, this single integral for the area. But now what we're going to do is we're going to rewrite it as a double integral. And it's actually, I think, really, really easy to go from a single integral to a double integral. Check this out. This way, we're going to rewrite it as the integral, and you don't usually have to write the things I'm about to write, but I'm going to write them anyway. So usually we just write 0 to 2, but I'm going to be more explicit and say we're going from x equals 0 to x equals 2. And then instead of writing 4x minus x cubed, the inner integral is going to be where y goes from the lower limit, which is x cubed, to the upper limit, which is 4x. dy dx. And then what are we integrating? We're integrating 1. So this will give us exactly the same thing. Because if we integrate 1 or antidifferentiate 1 with respect to y, what's the antiderivative of 1 with respect to y? It's just y. And then you would plug in y equals 4x minus y equals x cubed, and you'd be right back there. So when you're integrating double integrals, just like with partial derivatives, you kind of have a partial integration where you're only integrating with respect to y. So anything that's not y gets treated like a constant. But now, when you integrate a constant, you get the constant times the variable. Instead of when you differentiate a constant, you get 0. Similarly, this one could have been rewritten as the integral from y equals 0 to y equals 8. And then the insides are going to be the integral from a lower limit of x equals y over 4 to an upper limit of x equals the cube root of y. Still 1 dx dy. I always think of it as the inner thing, you get y equals paired with dy. The outer parts, you get x equals something paired with dx. Or vice versa, if you've done it this way. Here, the inner ones are x equals paired with dx. And the outer things are y equals paired with dy. It can feel kind of backwards, though, because most people would write this as the integral from 0 to 2, the integral from x cubed to 4x of something dy dx. So if you see x is here in your inner integrals limits of integration, you should have a dy first, because those x's are what y is equal to what y is equal to. Questions so far? So we could actually solve it, right? If we do this first one, we'd end up getting, so if we integrate this one, I'm actually gonna write out, even though I know it's already written up here, we're gonna get the integral from x equals 0 to x equals 2. We integrated 1, we got y evaluated from x cubed to 4x dx. We plug in, we get the integral from 0 to 2, bless you, of 4x minus x cubed, right? We're just plugging in 4x for y and x cubed for y. And then finally, we antidifferentiate this. We get 4x squared over 2, which is 2x squared, minus x to the 4th over 4. Evaluated from 0 to 2, we plug in. We get 2 times 4, which is 8, minus 2 to the 4th divided by 4, which is 16 divided by 4. Minus 0 is equal to 4. So that's how much area is actually there. But really what we are doing, although it is the area of the shape, what we're actually doing is we are actually calculating a volume. It's the volume of the shape that would have that base and a height of 1. And I'm going to try to draw it. It's probably not going to look great, but here's like my base shape kind of in the plane. And then the idea is that it just has a height of 1. So this thing here, that was our area there, that has a height of 1. We're calculating the volume of the region of the solid, whose base is the region we just calculated the area for, and whose height is 1. Which makes sense, right? If you have a shape that has like a base area of like 32 square feet and you multiply it by a height of 1 foot, the volume is going to be 32 cubic feet. We're just ignoring the dimensions here so that we get the right answer for the area, which is the same as the answer for the volume. So why would you do the area this way? Well, you really wouldn't. But the idea here is instead of having a solid whose height is always 1, we can now look at other solids and find their volumes that have heights that are interesting surfaces. So that's what we're doing with this. Is we're using double integrals to calculate the volume underneath the surface. For example, we're going to be sure, but I'm getting a little ahead of myself. We should practice a little bit more with just the easier things. So, yeah. So as far as Lee's class goes, I feel like almost all of his examples are super duper straightforward and kind of easy. I'm going to show you ones that are a little bit harder because that's what we usually talk about. But what I mean by easy is most of his examples, all the limits of integration are always just constants, meaning your region is always just a rectangle. I think that's too easy for you all. I think you can extend yourselves a little bit here. So let's look at this next example. We want to sketch the area, even though we know it's technically a volume, which is also known as the region of integration, or the region that we are integrating over, for the following double integral. The integral from 0 to 3, the integral from x squared to 9 of 1. Let me ask you all, should this be a dx then dy or a dy then dx? Right, it's got to be dy first because we know that this is y equals x squared to y equals 9. This is x equals 0 to x equals 3. So we want to sketch that region. So if I'm trying to sketch the region based on the double integral, I'm always looking from the inside out, which is also how we're going to integrate this, right? We're always going to integrate from the inside out. So we know that we're looking at graphing y equals x squared to y equals 9 first. So we're just going to graph those two things. So y equals x squared, usual parabola. Okay. And y equals 9, horizontal line. And it usually makes sense to think about or find the point of intersection. Here they're really easy, right? We know that if y equals 9 and y equals x squared, well, that point there has a y coordinate of 9 and an x coordinate of 3. No surprise. Similarly, over here, the x coordinate is what? Right. Now, don't get too hasty here. It's really tempting to just shade all that in because you're like, oh, it's the area between the two curves. It's not, because we're also limited in how far left and right x gets to go. So when I'm drawing this, y equals something to y equals something, I'm thinking of, okay, I'm going from a lower y to an upper y, so my strips are kind of like vertical things. I'm thinking of these being my strips. And then the x part tells me how far left and right they go. So they go as far left as 0 and as far right as 3. So I don't get any of this other half over here. It's just the right-hand side. So this is the region that we have described with this double integral. The interesting part, I think, or the part that's challenging sometimes is, and again, this won't really be a thing for the examples that Lee's class is seeing. Sometimes the process or the thing you want to do is to interchange the order of integration. So you want to re-describe this region of integration with now using a horizontal strip. If we use a horizontal strip, and again, let's work from the inside out. So if we change the order of integration. So then our inner integral is going to be the integral of 1 still. The integrand doesn't change when you change the order of integration. But then we know it's going to be dx dy. And we know that our inner limits of integration are, well, the left boundary of this green horizontal strip is the line x equals 0. And the right boundary is the curve y equals x squared, but we have to solve for x and say, oh, x equals plus or minus root y, but since we're on the positive x side, it's got to be positive root y. If it was over here, it would be negative root y. In fact, we should have done that one instead. Oh well. And then the second limits of integration, the outer limits of integration, are how low we go. Okay, we go as low as y equals 0. We go as high as y equals 9. So you can't just switch the limits of integration. You have to actually think about what the region looks like and then figure out what the curves are. Unless it's a rectangle. And if it's a rectangle, then you just get to switch them and it's super easy. So I will also point out that easier versions would be something like the integral from 0 to 3 of the integral of 1 to 7 of 1 dy dx. This requires absolutely no thought. You can just rewrite it as the integral from 1 to 7, the integral from 0 to 3 of 1 dx dy. Because in either case, what you're describing is y is going from 1 to 7, and x is going from 0 to 3. So we're getting this. It doesn't matter if I say that x goes from 0 to 3 first, and y goes from 1 to 7 second, or y goes from 1 to 7 first, and x goes from 0 to 3 second. If it's a rectangle, it's always just a matter of switching the integrals and switching the differentials order, and then you've rewritten the order. So, see, let me look at my examples before I start trying to get too crazy here. Yeah. So what can we do with this? Well, we can use this to, like I said before, find volumes under surfaces. So for example, do I have enough room to draw this picture? Yeah, I think so. We want to find the volume of the solid that lives in the first octant, meaning it's in three-dimensional space, and it's the 1/8 of three-dimensional space where everything is positive. X is positive, Y is positive, Z is positive. And I mentioned before, if that corner in the room is the origin, we are sitting in the first octant where X is positive and Y is positive and Z is positive. So find the volume of the solid in the first octant bounded by X plus Y plus Z equal to 4 and the coordinate planes, the XY plane, the XZ plane, and the YZ plane. So let's draw a question. Yeah. The reason we're doing the first octant here is because it's easy to describe the thing we're trying to find and to write the limits of integration. But yes, you can totally we will have shapes that exist in other octants as well. Or in other octants. Yeah. So let's draw the shape. It is fair, though, to point out that many of our examples do live in the first octant because it's easier to draw them. So for this plane, x plus y plus z equals 4, all of the intercepts are 4. So we're going to go up 4. We're going to go over 4. We're going to go out 4. So the shape I'm looking at is essentially the area of that tetrahedron. Sorry, wrong word. The volume of that tetrahedron. And so here's where my picture might fall apart a little bit, but the idea is that essentially the triangle that's in the XY plane is our region of integration. And the idea is kind of like with regular integrals, how we broke it up into a bunch of rectangles whose areas we were adding up. Now we're thinking about breaking up this area and then drawing a bunch of little rectangular prisms whose volume we're going to find. And we're going to add up all the volumes of the rectangular prisms. So our volume here is going to equal the double integral over the region of integration of our function. Oh, our function. Well, we're bounded by the plane x plus y plus z equals 4. So typically, if we're thinking about going from bottom to top, we're thinking about the lower thing being z equals 0 and the upper thing being z equals whatever the bounding function is. So we should take this and say, oh, we want z equal to 4 minus x minus y. And that's the top of our rectangular prism here. So that's our function that we're going to be integrating. That's your f of x, y, if you like. dA. This is the generic way of writing a double integral before you've decided which way you're going to order the limits of integration, whether it's x first then y or y first then x. So typically when we do this, then we like to just draw the region of integration in the xy plane. So I just draw what's happening in the xy plane. Well, I'm bounded by this, where that's 4, 0, and that's 0, 4. And if there isn't a good reason to do it one way or the other, I typically default to going dy dx, because I like to think about my strips being vertical, going from y equals something to y equals something, and then x going left to right. So I'm going to do this as the integral of the integral from y equals some bottom thing to y equals some top thing of 4 minus x minus y dy dx. I should draw my vertical strip here. My lower bound is y equal to 0. My upper bound is this line that goes from 0, 4 to 4, 0. Well, that line clearly has a slope of -1 and clearly has a y-intercept of +4. So that line is definitely y equals -x plus 4. And then the x limits are going to be, we can go as far left as 0, as far right as 4. So there's our double integral for the volume of this tetrahedron. Now we just have to do it. And I should give myself more room to do it than trying to squeeze it into this little space. A hard lesson for me to learn. So the volume is going to be the integral from 0 to 4 of the integral from y equals 0. And again, you don't have to write the y equals 0 here or the y equals -x plus 4, because it should be obvious that since there's an x in it, it must be y equals something to y equals something. But again, I don't think it's a bad thing to do. I think it's good to remind yourself of what's happening here. Also, the dy there tells us that as well. Right? The dy there is like, oh yeah, those first limits are y equals 0 to y equals that, and our outer limits are x equals 0 to x equals that. If you like, I don't particularly care to do this, but if you like, you can also completely surround the inner integral with parentheses to remind yourself, oh, we're just working with that inside part first. And then after we deal with it completely, we'll deal with the outside part. Okay, so I'm anti-differentiating with respect to the variable y. Yes. Oh, sure. So I'm looking at my region of integration, which is the region in the xy plane. And in the xy plane, right, this point's 4, 0, 0. This point's 0, 4, 0. This point's not in the xy plane, but the 0, 0, 4. If I just look at that triangle in the xy plane, that's this triangle here. And so when I think about my y limits, my lower limit is y equals 0. And my upper limit, I did it kind of fast. I said the equation of this line, well, the slope clearly has to be -1 because we're starting at 0, 4, and we're going over 4 and down 4. So our slope's -1. And then the y-intercept is +4. So our equation of our line is y equals our mx plus b, which is -1 times x plus b. That's where that's coming from. And sometimes it takes a little bit more work to find the thing, but usually if it's a straight line, it's usually not too terrible. So then we remember that we are anti-differentiating with respect to y. So anything that's a constant, its antiderivative is going to be that constant times y. So when we do this inner step here, yeah, I like these parentheses. I know I said I didn't like it, but I might have been lying. I kind of do like it. Lying to myself. So when we integrate 4 minus x minus y, we get 4y minus xy minus y squared over 2, evaluated from 0 to negative x plus 4. Right? Each constant thing, 4 and x, when they anti-differentiated, you just multiply them by y, and then y, which is the variable, you use the anti-power rule. So now we're going to plug in our limits of integration. This is where things get kind of gross. So we still have the integral from 0 to 4. We're going to plug in negative x plus 4 for y and get 4 times negative x plus 4 minus x times negative x plus 4 minus negative x plus 4 squared over 2. And then minus, if we plug in 0 for y, every term will be 0. 0 minus 0 minus 0. So we don't really need to write that. I do think it is definitely in our best interest to simplify this before we try to anti-differentiate the next part. Sorry, something weird there. So let's multiply this out. That's going to be equal to the integral from 0 to 4. I've got negative 4x plus 16 minus x times minus x is positive x squared minus 4x. And then minus negative x plus 4 squared is going to be x squared minus 8x plus 16 divided by 2. I think it's worth it to simplify it. One more step. So let's see. I have an x squared minus x squared divided by 2. So that's 1x squared minus a half x squared, which is also going to be a half x squared. And then I've got a negative 4x minus 4x, which is minus 8x. And then I have a plus an 8x over 2, which is a plus of 4x. So I'm just getting minus 4x. And then my constant term is 16 minus 16 over 2 is 8, and 16 minus 8 is 8. And now we're ready to integrate. So we're going to get 1/2 x cubed over 3 minus 4x squared over 2 plus 8x evaluated from 0 to 4. We could probably simplify that. It's going to be x cubed over 6 minus 2x squared plus 8x, 0 to 4. We're going to get 4 cubed divided by 6 minus 2 times 4 squared plus 8 times 4. And I'm going to at least mentally check that if I plug in 0, okay, I plug in 0, yeah, that's 0 minus 0 plus 0. I was definitely helping someone in a different class the other day where they're doing a web work problem and they totally didn't check the 0 part there. And they're like, well, why isn't my answer right? Because you didn't plug the 0 into the other part and get that cosine of 0 there isn't 0, it's 1. So make sure that if you're not writing anything after that, you have checked that when you plug in 0, yeah, all the things are 0. Okay, we're good to go. So that's my answer. And I guess we could simplify it. That's going to be, well, those actually cancel, negative 32 plus 32. So we end up getting 64 over 6, which reduces to 32 thirds. And that's the volume of that tetrahedron. Kind of neat. Thank you. Okay. So one thing we do with double integrals, aside from volume, is also talk about finding the average value of a function over some region. So I think in 17b, we talked about average value for a second, where it's just the integral divided by the length of the interval. The same thing is going to be true for double integrals. But now the average value, instead of being the area divided by the length to get the average height, it's going to be the volume divided by the area to get the average height. So we're taking, instead of dividing a two-dimensional thing by a one-dimensional thing to get a one-dimensional thing, we're dividing a three-dimensional thing by a two-dimensional thing to get a one-dimensional thing. It's easy to calculate once you know what you're doing. It's really almost the same idea as before, just with a slight twist. So let's give ourselves the following setup. The amount of rainfall per year in the triangular, I can spell, area bounded by the points 1, 0, 5, 0, and 5, 4 is given by f of x, y equal to 6 divided by x times y plus 1 inches. So whatever coordinate you pick, like if x is 1 and y is 1, then you're going to get 6 divided by 1 times 2, which is 3 inches per year. Okay, at that one point. So first, we're going to find the total amount of rainfall for the year, or in a year, over the region. In other words, find the double integral of the function f of x, y over the region that they described to us. So let's draw the region. My points are 1, 0, 5, 0, and 5, 4. So here's another triangular region. Triangles are like the next easiest thing after rectangles to have your region be. So our volume is going to equal the double integral over the region R of our function dA. Again, starting just with a very, very generic way of writing it. And then I suppose I really don't like doing it the other way. We could do it in terms of x first, like with a horizontal thing, but I don't think we should do that unless we need to. I would always default to a vertical strip first, meaning I know that my volume is going to equal, well, my outer limits, and I know I usually start with the inner limits, but I'm just going to do the outer limits first because I know that if I draw this vertical strip, it's going to go as far left as 1, as far right as 5. So my x limits are from x equals 1 to x equals 5. My y limits, well, again, we have a lower boundary of y equals 0. And I want you all to find the equation of this line that's our upper boundary while I write the rest of this. So a lot of these triangles are going to have a slope of 1 or -1. This one also does, right? We're going over 4 and up 4, so our slope is 1. And then you can find the equation by saying y minus the y coordinate is equal to your slope times x minus the x coordinate. So we get y equal to x minus 1. So that's our upper boundary. Now we're going to integrate. So what I see here is I'm thinking of this, if I'm integrating with respect to y first, I'm going to think of that as 6 over x, a constant multiple of 1 over y plus 1. That constant multiple is just going to hang around, and the integral of 1 over y plus 1 is going to be the natural log of the absolute value of y plus 1. So when we do our first inner integral here, we're going to end up getting still the integral from 1 to 5. And then my inner function, well, I'm going to have 6 over x just hanging out. And the antiderivative of y, 1 over y plus 1 is the natural log of the absolute value of y plus 1. Evaluated from y equals 0 to y equals x minus 1. Still with a dx. Then we're going to plug those things in for the y's, right? Only for the y's, not for any of the x's. And we're going to get still the integral from 1 to 5. We have 6 over x hanging out. Plug in x minus 1, we get the natural log of x minus 1 plus 1, which I'll write the absolute value of x for a second here, minus the natural log of 0 plus 1. But that's the natural log of 1, which is 0. Now, technically, I don't need to write the absolute value of x there because limits of integration for x are all positive numbers, right? We're starting at x equals 1, we're ending at x equals 5. X is already positive. You don't need to write the absolute value of x. So now we are trying to integrate from 1 to 5. Let's pull the 6 out in front. The natural log of x over x dx. Looks like a u substitution. I know it's been a while since doing a u substitution, but it's a u substitution. If we let u equal the natural log of x, our du is exactly 1 over x dx. So we can totally rewrite this as 6 times the integral of u du. And since it's a definite integral, I might as well change my limits of integration. If x is equal to 1, that means u is going to equal the natural log of 1, which is 0. And if x is equal to 5, I'm running out of room here, I know. U is going to equal the natural log of 5. And then we can integrate. We get 6 times u squared over 2, evaluated from 0 to the natural log of 5. We simplify and we get 3 times natural log of 5 squared minus 3 times 0 squared, which is just going to be 0. So that's our total rainfall over this region for the year. And if I wanted to find the average amount of rainfall for a particular like square section, that's not really a great way to phrase that. Yeah, that's not, I don't love that. Yeah, but sorry, the phrasing of this sounds weird in my head. Because when you talk about average rainfall, you don't think about it. I know I started talking about average value and then that's, yeah. So let's say the average value of this function, f of x, y equal to 6 over x times 1 over y plus 1, or 6 over x times y plus 1 as I originally wrote it, over the triangular region that we described, with vertices 1, 0, 5, 0, and 5, 4, is really easy to calculate once you've done the double integral. It's going to be the following. It's equal to the double integral over your region of your function divided by the area of your region. So just the double integral we already did divided by the area of that triangle. Now, depending on how complicated your region is, sometimes you have to do it like this. You're like, okay, well, it's the double integral over my region of my function, which we already calculated, divided by the double integral over my region of 1. But only if your region is kind of funky. If your region is a triangle, we know how to find the area of a triangle, right? The area of our region in this problem, well, it's 1/2 times the base of our triangle was 4. The height of our triangle was 4. So the area of our region is 8. And then our average value is going to equal the total volume that we just found divided by the area of our region. So it's really, really easy to do, just like it was when we did average value back in 17B. You just take the value of your integral, and instead of dividing by the length of your interval like you did before, you divide by the area of the region that you're integrating over, but still the same concept. Sure. Let's call it a day. The whole 6 minutes to spare. Yeah. We might talk more about double integration on Monday, but there's not a whole lot. There's one more thing to kind of say, and then we kind of, again, like I said, it's not something we spend a whole lot of time really doing, and I don't see a lot of value for it, other than it's a good thing to be able to do, but as far as the rest of the class is concerned, I don't see where it comes back up. I don't think it does. I'm pretty sure it doesn't. All right, for those of you that have a test, good luck. I have office hours if you want to come see me, and have a lovely weekend. I'll see you all on Monday. Yeah, sorry. Oh, sure. Yeah. So for the u sub part, all right, I was doing the integral of the natural log of x over x dx from x equals 1 to x equals 5. And so I said u equals natural log of x. Du is 1 over x times dx. So I rewrote this as, I should say, I thought about rewriting it as this. And then my 1 over x dx became du. My natural log of x became u. And since it's a definite integral, I changed my limits of integration. So if x is equal to 1, u is going to equal the natural log of 1, which is 0. And if x is equal to 5, u is going to equal the natural log of 5. My new limits of integration, instead of x equal to 1, I get u equal to 0. Instead of x equal to 5, I get u equal to the natural log of 5. Yeah. And then we integrate, we get u squared over 2 from 0. And there was a 6 out in front. Sorry. We get 6 times u squared over 2 from 0 to natural log of 5. I simplified this as 3u squared. And then plugged in, I got 3 times natural log of 5 squared minus 3 times 0 squared, which was just 3 times natural log of 5 squared. Yeah, no, I know I went a little fast there. Sorry. Yeah. So the office hours today are in PADS, which is the Center for African Diaspora Student Success. It's located in the South Silo. So it's not like not the main silo, but like the one kind to the left, where the silo market is. So the silo, like if you're going into the silo market front doors, you just go to the right. Around the corner, there's a doorway with a stairwell. You go up the stairwell. Yeah, up the stairwell, in the door to your right, and then you'll see it. There's a sign. Right. You really can't go after you go up the stairwell and through the door there. You can really only go to the right. And I'll be there shortly. Yes.